There were, well, there was at least one request today, but in the past there was a couple of requests for me to go over the op-amp stuff, which includes cascoding, a folded cascode, gain boosting, and that's because I think half the class was gone that day. So here we go. Now that we know the basic amplifiers, and since we're trying to build an op-amp in this class, one of our real interest is how to increase the gain. So here's where we're going to look at how to increase the gain. And it turns out GM, there's not much you can do with GM. Big GM is almost always the little GM of the transistor that the input goes into. The only time it isn't is when there's degeneration. So generally, if the emitter had a unmoving node, then the GM of your entire amplifier is just going to be little GM of that input transistor. But what you can change is the R out. We started with a common emitter and we had a resistive load, and then to increase that we increased that resistance. To increase the gain, and then when we got to the limit there, because if you increase the resistor too far, now you turn the transistor gets put into linear. So there's a limit to how big you can make that resistor. With, I mean, of course you can raise the supply, but now you're using more power, and all sorts of other things get harder. So that has a limit to how much you can use a passive load, or how much gain you can get with a passive load. So next said, okay, how about an active load? Okay, so that's what we did next. And so that was two ways to increase the gain. But there are others, and that's what we're going to do here. One's cascoding and one's gain boosting. And the folded cascode is kind of folded into the cascoding here. And we've already seen one other way, and that's called cascading. And cascading is good because you can get a big gain with a low supply voltage. You just string together a bunch of lower gain amplifiers and they multiply each other, so you get that big gain. The problem is that you get lots of poles. Frequency response is a little more complicated. Now you have 4 amplifiers to bias instead of 2, or things like that. The design just gets a little more complicated. Okay, so cascading is good for low voltage, but this video is about these two things right here. Cascoding, and cascoding with an O. So not cascading. Cascading is where you string the amplifiers together. Cascoding is where you stack transistors together. And what you'd think is if you're sitting on this V out and you look down, you'd see one RO and then another RO. But with cascoding, what you get is actually an RO squared. Well, for MOSFETs you get an RO squared. For BJTs you get an R pi times RO. So it multiplies instead of just adds. And one very common error people make is they put V in on this second transistor. If you do that, just think about it. If you had V bias onto here, this thing right here, the R pi would, well, this is an infinite R, but VGS, because when you do small signal analysis, this becomes a ground. Now VGS becomes 0. The current source goes away, and now you just have RO here, which gives you degeneration of your amplification, which kills your gain actually. So what you want to make sure with when you're doing cascoding is that Vin is on the bottom. So if Vin's up here, this turns into resistor, and all you're getting is degeneration, which actually kills the gain. It has the opposite effect. Okay, so this is cascoding. You get an RO squared out. Okay, and if one important thing is, let's say I cascoded right here. Now looking down, I get an RO squared. So when somebody asks me what RO is, it's whatever looking down is in parallel with whatever's looking up. Okay. If I just have a resistor up here, say 1,000 ohms, and I just increase this one to RO squared, which could be millions. when I increase this to RO squared, if there's just a resistor looking up, what you get is the resistor in parallel with that RO squared, and all you really see is this resistor. So it didn't help you that you increased this. So to get, remember, we're trying to increase gain. We're trying to increase gain by increasing R out. What we want to do here is to get that big R out, we have to not only increase the R out looking down, but we have to increase the RO looking up. And you generally want to try for same RO looking up as looking down. Because if you have one bigger than the other, then that big one is just wasted. Okay, so RO squared looking down, RO squared looking up. Now your R out is RO squared over 2. Okay. And one term that I have not mentioned is, yes, it's RO squared, but it is multiplied by the GM of the second transistor. So the approximation that people use for this resistance is it would be GM3, small GM3, RO looking down in parallel with GM5 times RO, just GM RO squared. So one of these GMs, it actually comes out to a combination of these two, but GM RO squared. Okay, so same problems. This has the same problems that common emitters have. It's very sensitive to VN. VN's a little bit too high. V out rails one way, VN's a little bit too low. V out rails the other way. So you have to be very careful when you're biasing this right here. Way to solve that is to put that into a differential configuration. And remember, differential configurations, you have that VIC. This node right here can move around to set the VBEs here. Okay, and what it sets the VBEs to, or VGSs, I'm sorry. What it sets the VGSs to is 1/2 ISS. Let's say you had both of these inputs set to the same thing, then these VGSs would move to where that VGS will conduct ISS over 2. And this doesn't really care, because if this is in forward active, it doesn't really care what its drain voltage is. Same story as BJTs. Okay, so if you put it into a differential configuration like this, now it's much easier to bias. Okay, just as long as your two inputs right here move around the same value. And just like in lab, you can set one of these to a voltage, and then they have the other one move around it and have unbalanced inputs, in other words. Okay. This configuration, the differential cascoded amplifier, and we call these op amps now just because they have such a large gain. And remember, one of the conditions of being an op amp is that it has a big gain. So these are considered good gain stages for op amps, I should say. It doesn't have a small R out, so it's not a good op amp, but it's a good gain stage for an op amp. Okay, so this is cascoded. It's differential. So differential cascoded common emitter amplifier has a special name. It's called a telescopic op amp, or telescopic amplifier. And the reason is that it's long. It's really tall. It's got 1, 2, 3, 4, 5 transistors stacked on top of each other. So the supply voltage has to be high enough to accommodate all of those. If these were BJTs, then you'd have 1, 2, 3, 4, 5 VCE sats. Okay, and that's the lowest voltage the supply can have and still have everything in forward active. The thing is, if you bias this at 5 VE sat, then V out can't swing at all. So generally, VSUP has to be 5 VC sat plus whatever your output swing needs to be for your amplifier to work. Okay, so this is telescopic, and I don't remember. Did I write that out? Okay. This is just the analysis of cascoding, and what you can see is you get. I'm not sure if you can see this actually, but you get an RO1 times RO2 and then GM2. So that second transistor right there. So GM of that second transistor times the ROs of each of those. Okay, then I really should have this labeled. This should be labeled. We'll So should I make this? Actually, let's do felt tip pin, and then let's do equals, well, no, this one. This is telescope. Okay, so that's telescopic. Okay. Whoops, I guess that's not the best place to put it. Okay, and then the calculations of why it's RO squared. Okay. All right, so that's we're done with telescopic. Okay. Cascoding and telescopic. Okay. There's another way to increase gain, and if you remember, we just said that if you have a cascoded, two cascoded amplifier transistors, then the R looking down is RO of this one times RO of this one times the GM of this one. So that's what you get right here. Here's GM, here's M1. So the transconductance of this transistor times the RO of this times the RO of that. Okay. Gain boosting. Gain boosting is kind of an interesting way. You're still increasing this R out, but the way you're increasing this R out is by increasing the GM of this transistor right here. Let's let's keep. Okay, so let's go to see where this comes from. So we have. I'll stay, since those are MOSFETs, we'll just stay with MOSFETs. And this is where we're going. Still have V in on the bottom. And this can be part of a telescopic or just a plain old cascoded. So it can be part of. It can be part of either one of these. And what I'm going to do here again is the equation for R out, looking down, has this GM here. I'm going to increase the GM of this second transistor here. So this is where we're going. But let's look at a simpler, let's compare the GM of these two configurations. Let's do V in. Okay, now this is a little bit separate from this circuit, but let's compare the GM of these two things. Okay, so if you remember, definition of GM, that's supposed to be an equal sign. That's I out over V in. Got V in marked really clearly, and I out is, I guess you would define it in that direction to be correct. And this would be I out for this circuit. Okay, so let's see. If I move V in right here, let's say I raise it, that increases VGS and increases the current through the transistor. Okay, and if you remember, when you're in a small signal region, everything is linearly proportional. So the change in I out, equals V in times some constant, and that constant is just the gain. How how should we do this? Let's move. Say it's times some constant. Vn let's do this. There we go. We're cheating a little. Proportional to Vn. So change in I out is proportional to the change in Vn. Should actually say change in Vn. Let's try this. Let's go back over here. So it's proportional to the change in Vn. Okay. Let's see. So current out is proportional to the change in Vn. Okay. Now let's look over here. Let's say, and let's say I change this change in Vn here. So I move this note Vn up. Let's say I move this up by the same amount. Question is what happens to this node? And the answer is, because this is an amplifier, this change gets multiplied by the gain of this and shows up here. So it's actually whatever the gain of that amplifier is times the change in Vn. And I'm kind of not, I should have deltas in here, but if you move this half a volt, this gets moved half a volt times whatever the gain is of this amplifier right here. So AV times delta Vn. Okay. I move this up half a volt, this moves up, let's say the gain's 100. Okay. If I move this up half a volt, if the gain's 100, then this moves up 50 volts. Okay, so a little move here makes a big move here. All right, if I have a big move here, that means my VGS is changing a heck of a lot. Moving a lot. Over here, when I changed VGS, it was just exactly that change. The change in VGS is the change in VGS. But if I change this V in here, change in VGS is AV times whatever I changed right here. And if the voltage across VGS changes AV times as much, that means since the current here, if we're in a legal linear region, the current here, the change in the current changes by AV times as much. So let's do this. Okay, so the voltage changes AV times as much as here. The voltage change AV times as much as here. Since this isn't, if this isn't a legal small signal region, that means the current changes AV times as much. So whatever this delta I was out over there, it increases AV times that amount. AV times AV times delta Vn times whatever that constant is. I'm trying to think of a correct way to say this. But hopefully, if you were all sitting there, I could see if you were nodding. But just by this voltage moving AV times as much, in the legal small signal region, everything is linearly proportional. So that means the current changes AV times as much. Okay. So let's go back over here. Here's our definition of GM. Here's, this changes some delta I out. That gives you the GM of this. But the current over here, this changes AV times as much. So what you get for the GM over here is whatever you had before. By putting this amplifier in here, you get AV times what you had before. Your GM increases by AV. And at the review session, ask me questions about this if this doesn't make sense. But I think if I just keep repeating myself, I'll just keep repeating myself and won't do you any good. Okay. By adding this amplifier, you get AV times as much current out of this thing for the same change in Vn. So your GM actually increases by AV. Up to there, I'm going to go back to the slides, I think. All right, so going back to the slides, what that says is, since this GM is the GM for this, by adding this, I can increase the GM AV times. So, oh goodness, let's see. Let's fix this. This should be How about that? That looks better. Okay. And this also should be okay. All right. So yeah. So by adding this, you get a GM that's AV times bigger than without this. And remember, this is the GM of this transistor, so it shows up in the R out. Even though you're changing a GM, that GM shows up in the R out equation. So you're actually changing R out. So you're changing a GM in order to change the value of R out. Okay. So that's gain boosting, and that's pretty complicated. In the example, what I did was I held this node unmoving. I had that as an AC ground, and I moved this node. But what actually happens in real life is this node is connected to V bias, so it isn't moving. And when you change V in, this node actually moves. But it's the same thing. You're changing the voltage across here. And then I'll leave the rest of the questions for the review session. Okay, gain boosting, oscillators. Okay, there's gain boosting. There's cascading. There's cascading. There's cascading. Cascading, not cascading. MOSFET stuff that we didn't get to. I'm sad. We do that. Here's just a biased telescopic op amp. Now for folded. Here's a folded. Okay. So the telescopic op amp, the problem was that it had 5 transistors stacked on top of each other, and that meant that your supply voltage was going to be at least 5 VC sat high. Okay. What a folded does is it takes one layer of transistors out, so you end up with just 4 stacked transistors. It's not all that much of a gain and improvement. You'd get to drop your VSUP by a VC sat, and you also lose some of your gain. So it's not all that big a win, but if you just need to drop your supply voltage by a little bit, that can help. This is one technique to do that. Okay. So let's look at this. You have, let's say we have IREF through here. We have IREF through here. And this is biasing circuitry, and you can see this is a little more complicated than you've seen before, but you have a diode connected, another diode connected, resistor diode connected. So this is, for whatever current's going through here, this is the VGS for that current. I'm putting that VGS on here, so you get IREF through here. You also have that same VGS here, so you get IREF through here. Let's do that. So you're going to get, this is going to be IREF. And this is also going to be IREF. And this will also be IREF. Well, I guess I should do that a little. Let's do red again. And let's do... Okay. So this is going to be IREF. Well, it's not much difference, but... Okay. And this is going to be IREF. And this is going to be IREF. Okay. And then you can also see you have got IREF going through here. Here's another diode connected transistor that's connected up over here. And so this is also going to have IREF. And I should be writing the I as capital since it's a DC voltage, DC value. Okay, so you've got IREF through here, IREF, IREF. Okay. I've got something interesting here. That IREF goes and it splits between 2 sides. This looks just like a differential pair. You've got your tail current source. Now it's a P device. It's like a flipped over diff pair. Okay. So it looks just like that. You've got your tail current source of IREF, and then it gets split between these two. So if V1 and V2 have the same voltage, you'll have IREF over 2 going through both sides. Now look at this. It comes over here. comes over here. So let's follow the current through here. It goes through here, over here, and then should go down. And remember, this is Iref over 2. Remember, this is Iref. Okay? The current through this branch and the current through this branch have to add up to Iref. So if this is Iref over 2, that means that by default, this is also going to be Iref over 2, as this side is. That's going to be over 2. Okay, so now this gets Iref over 2, because physics kicks in. It knows it has to sum to Iref, and it's getting Iref over 2, so this has to be Iref over 2. Same thing over here. You have Iref over 2. This has to sum to Iref, so you know that through this branch you also have Iref over 2. Okay, so far nothing really interesting has happened. You just have Iref over 2 summing with Iref over 2 to make Iref. Okay, let's do something here. Let's raise the voltage on this input. So on V2, let's raise that voltage. And remember, this is a P device, so if you raise this voltage, it's going to drop the current through there. Let's say we hold this constant. So unbalanced input, let's say we hold this constant, and we raise this. That means the current through this side is going to drop. It's going to drop some amount of current. And remember that the currents, the sum of these two currents have to equal Iref. So if this side drops by delta I, you know that this side has to increase by delta I. So you know if the current through this side drops by delta I, this side has to increase by delta I. So they sum to Iref. Okay, up to there. Okay, now remember physics is helping us out here. Now let's see, here's the wire coming in. This used to be Iref over 2, but because I raised V2 a little bit, now this current is a little bit smaller than Iref over 2. But remember, it has to add, it has to sum. The current through this branch and the current through this branch has to sum to Iref. So if this is less than Iref over 2, okay, then this current right here has to increase. If this drops by delta I, this current right here has to increase by delta I. Okay, so if the current through here drops by delta I, it has to sum to Iref. If this current drops by delta I, this has to increase by delta I. And let's see what happens over here. If this increases by delta I, remember this has to sum to Iref. So this side actually has to decrease by delta I. Now that's really hard to read. So what you had is you had your original current, and now you have to subtract delta I. This side is actually more than our Iref over 2 now. Okay. Well, so what does this do for us? Think of just a plain old differential pair. Think of a plain old differential pair. And now I'm trying to get BJTs. I should probably draw a cascoded diff pair, but I'm being a little bit lazy. So I'm just drawing a single transistor diff pair. Okay, let's see. When I raised this, what happened to the? Let's see. I should have probably put them on the other side here. But if I raise this, what happens to this node? If I raise this, more current goes through here, and V out minus drops. Okay. So if I raise this, the current through here increases. Let's go back to the slide for a second and see what happens. Okay. when I raise this, what happens to the current through this branch? It increases. Okay, go back to this. When I raise this, the current through this branch increases. So the exact same thing is happening by the exact same amount of current. What happens here is that you're raising input V2 and you're getting an increase in current. That's exactly what happened with the diff pair when it wasn't folded. So this is just another mechanism to turn up the current or turn down the current through the branch here. Okay, and you've gotten rid of one stack transistor there. Okay, so the other thing that I mentioned about this is that the gain drops a little bit. GM, if it's not if the input transistors are not degenerated, and this one isn't. Remember, if this is balanced, this becomes an AC ground. If these aren't degenerated, then the GM for your whole amplifier is almost always, if not always, the GM of your input transistor. So your GM for this amplifier would be the GM of this transistor right here. Okay. So it's and the gain is always big GM times big R out. So big GM is just the GM of this transistor. Your R out, you see RO squared looking up, but looking down, if you look at it, you see an RO here. But this, instead of seeing an RO, you have two branches the current can go through. And if you have more than one branch, that means you've just put something in parallel and your resistance has dropped. So because of having this second branch out here, the R out drops and your whole gain drops. And and this is from a simulation for the cascoded, in other words, the telescopic. I should write this as telescopic. Got a gain of 336,000, and for the folded, I got about a third of that. No more than a third. And that was because the RO dropped. Okay, so I think that is, we're not going to do the MOSFETs, because again, not quite sure. I know we had fewer lectures this quarter, plus we lost one to holidays, so it was like 2 or 3 lectures shorter than other quarters. So I think that was my challenge. If we would have had like one more lecture, we would have been okay with the feedback, but I feel like I shortchanged you a little bit on some of these topics. But hopefully that will answer some of the questions on the amplifiers talked about in that one lecture.